So in this video, we're going to look at measuring internal resistance. So we can create a circuit as below. What we do is basically we alter the resistance of this variable resistor. So what we've got is this is our cell here. Essentially what this voltmeter is connected over forms our cell. So that's what this is. And what we're saying is that we basically connect that up to a voltmeter, and then we connect it up to a variable resistor too. So basically we're measuring the potential difference across our cell, the terminal potential difference. And we're measuring the current through this circuit, and we've got this variable resistor here, which we'll just put R, but here the resistance varies obviously because we're free to set it. And what we can do is basically we can vary the potential, but we can't vary the potential difference, excuse me. What we do is we vary our resistance of our variable resistor. We change this, we take it up or down as we want, and what that's going to do is going to change the terminal potential difference and the current through our circuit. Why is that? Well, we saw previously that we know that clearly changing the resistance of this will change the current in our circuit, because changing the resistance will change the total resistance of our circuit and therefore will change the current. But what it's also going to do is change the terminal potential difference, because we saw, if we go back up previously, we saw here that our cell EMF is equal to our wasted potential difference plus our terminal potential difference. And so actually if I rewrite this, because this might be kind of surprising, right? Why should changing the variable resistor change the terminal potential difference? Why should the potential difference across our cell change with the outside resistance? We're kind of used to the idea that whatever the terminal potential difference across our cell is kind of a fixed thing, and what happens is that the total potential difference across our components is always just equal to the maximum, the sum of the potential differences, the potential drops across our components is just equal to the total terminal potential difference. But here, that's not the case anymore. What we see is that actually, because we know that epsilon is equal to the potential difference across our component here, which I'm going to call the terminal potential difference V0, that is going to be equal to, so our cell EMF is equal to that, plus the current times the basically our wasted potential difference, this I times little r, if we say the current in our circuit is I, as we normally do. So what we can do then is we can rearrange this equation to see that V0, our terminal potential difference, is going to be equal to our cell EMF epsilon minus this IR. And then we're going to talk about this more in a second, but I just wanted to set out the idea why changing this internal resistance, why changing this would affect things, because remember this is going to be IR. Sorry, that's not what I mean. Forgive me. What I mean is that this I here, forgive me, that changes as we change our resistance. What happens is as this R changes, clearly we're going to change the current, because as we change our this is fixed. Excuse me, what I mean to say is that this cell EMF is fixed and this internal resistance R is fixed, but this changes with R.
Hey guys, to continue watching this video and unlock hundreds of other super concise and exam board specific A-level physics videos, just click the Snap Revise smiley face. Join me today, and together let's make A-level physics a walk in the park.